Okay, so I'm back to cover the second half of problem set 13. So this is done in parallel to the virtual class session. I do anticipate redo a lot of these questions at the virtual class session today. I'm creating this recording right now more as a backup because the time between when the virtual class session ends and when this homework set is due is rather close. So yeah. So um, I guess without further ado, I'll get started. We are continuing with the problem set 13, which is the wave mechanics wrap up and a pretty long set. This is the second half of the set. Question 8 is where I left off. So let's take a look at here. It says, yeah, goes without saying that solving differential equation is not easy. Read through that. And really, the purpose of this particular question is to help you build up your intuition. So, so working through here to solve for the second derivative of the wave function, which will help us to see some behaviors of the solution more easily. Yeah. So let's just answer part by part. So it's pointing on this coefficient here, k minus 2m, difference between the two energies. So in the region where the total energy is greater than the potential energy, this entire coefficient, it should be negative because this combination is positive, but there's this minus sign here. So the whole thing is negative. And the signs of k and psi x give the overall sign of the right hand side here, and hence the sign of the second derivative, which relates to the curvature of the function. Is it concave up or concave down? And this is a bit of a calculus review, I guess. This is something that you should have learned in calculus 1, I think. So you imagine a function psi of x, which let me just plot something that I don't know, looks like some arbitrary function here. Um, so if I have something that looks like this, I don't know. It's just an arbitrary function. I'm not really doing anything here. Um, when you look at in this region, for example, what you should see is that the slope of the function, so let me draw a tangent line here, is changing upward. So in this region, what you should be seeing is that the second derivative is positive because the change of the slope is in the positive direction. So here, I would say, so this is where I would call it concave up. So for the situation that's described in A, where it's a negative, that's better described by behavior that's maybe seen here. Here you can see that the slope of the function, it's sloping, it's changing in the negative direction. It's becoming more steeper downward. So here the second derivative, which describes the rate of change of the derivative, would be negative. And this is what you would call concave down. So calculus review. So you would say concave down. Considering the same situation above, if oh yeah, I guess I without thinking too much, I drew it for the situation where the wave function is positive, and yeah, when the wave function is positive, there's nothing surprising here. In part C is where you have to be careful. Imagine if the wave function is negative. So if this part is negative, then this right hand side as a whole is actually positive, which means the second derivative is now positive. So it would be concave up. And combining B and C, where it asks which description below best describes the behavior of psi. when E is greater than U of X in one phrase. Let's just go through each choice one by one. Psi of X is an odd function. I don't think I have enough to say that because odd means when I replace x with minus x, the whole function changes to minus of its previous. And I don't think I have enough evidence to say that. Psi of x always curves away from the axis. Hmm. Okay, second derivative does describe curvature, but I would describe this as curving towards the axis, not away. So let me skip that for now. Psi of x is asymptotically approaching a non-zero value. I don't get that feeling by looking at this behavior here. It's not asymptotically doing anything. If anything, it's plunging towards zero. So psi of x is an even function. Same comment as an odd function. I don't think I have enough information. Psi of x always curves towards the axis. You can actually see it here. When you look at the this portion of the curve, it's concave down, it's curving towards the axis. And imagine that this wave function somehow went beyond the axis. Then as we described in C, this would be now concave up. So it's again curving towards the axis. So where the energy, total energy is greater than the potential energy, the wave function always curves towards the axis, and that should result in something that's oscillatory because when the wave function is above the axis, it's curving down towards the axis. When it's below the axis, it's curving up towards the axis. So, okay, what if the energy of the um, total energy is less than the potential energy? Then what I think you should do is work through BNC equivalent of BNC or A BNC again. Your answer to A would be negative. Sorry, positive. If E is less than U, then this K as a whole is positive, which would mean if psi of x is greater than zero, then it would be concave up, almost like this portion of the wave function. But one thing you do have to be careful is if this behavior continues to x approaching infinity, that gives you an unnormalizable function. So really the other thing that would work out here that's still concave up but would give you something normalizable would be something that looks like this, an exponential decay that's concave up and you would vanish to zero so that you can normalize it. So with all of that in mind, the answer here is basically opposite of the answer in D. So psi of x always curves away from the axis in the region where total energy is less than the potential energy. And the note here. So in the case where this is constant, you see the two familiar solutions you have seen in the lecture. One is the sinusoidal oscillatory solution. The other is the exponential asymptotic or um, the exponential decay function. Oh, and it's not asymptotically approaching a non-zero value because it should be approaching zero. If we approach the non-zero value, uh, like constant function is not normalizable either over all space. So yeah, those are almost a conceptual question, and I guess in this class we don't really make a lot of use of it, but in upper division, in some versions of semi-classical analysis, particularly what's called a WKB approximation, this level of intuition ends up being very helpful. Um, but for this class, we don't really do a lot with it. All right, so I think questions 9 and the rest are more detailed questions. So let me go through these in detail. So I think this is the first of a three-part tutorial, but the first part doesn't mention it. We'll just work through it. It says reflecting from step-up potential. Okay. It says following a tutorial for solving Schrodinger equation. So let me just start by sketching things out. So question 9 is Schrodinger equation for the following potential. Let me sketch the potential. So I guess I want to put x equals 0 somewhere reasonably in the middle. And the potential function looks like a 0 for the negative axis. And then at x equals 0, it suddenly jumps up to a value of a constant value, u naught. Okay, where u naught is positive constant. Yeah, think of this left half the barrier. Follow this tutorial to derive the reflectance of instant particles of energy E greater than u naught. Okay, that's good to note. Let me just draw a line to indicate the energy of the instant particles and answer some conceptual questions. For the region x less than 0, the Schrodinger equation takes the form, right, it's been solved for the second derivative and the potential is 0. Okay. The second order ordinary differential equation has two linearly independent solutions. Yeah, so if I had to find a solution to um, an equation that looks like this, second order derivative is equal to, let me use a constant k to represent this, minus k psi of x, actually, sorry, k squared psi of x. Then I would stare at this for a while and immediately come up with this or guess this solution that I have seen, I have used in other contexts before, which is this general solution. Psi of x is equal to some integration constant times exponential of plus ikx plus b times an integration constant exponential of ik, oh sorry, not ik, minus ikx. Equivalently, you can also write this in this form. This is more of a taste or whatever. You can write an equivalent solution in this form. Psi of x is equal to some constant times cosine of kx plus some another coefficient times sine of kx. Or actually, there's one other way to write it, which would look like psi of x is equal to, let me call it E times cosine of kx plus phi. Because there's so many different ways of writing solutions to general solutions to this particular differential equation. In the question text, I'm giving you enough descriptions to narrow down these possible forms of solutions into a particular one that can actually be graded. So it's saying, okay, where necessary, use the value of 0 or 1 for integration constants. Okay, so whatever I do, I'm gonna end up with something like a is equal to b is equal to c is equal to d is equal to e is equal to 1. So I'm not gonna bring up those constants. Um, and then here it says general solution with positive value of momentum. And this is where it helps to remember the momentum operator. Momentum operator is minus I times h bar times the derivative with respect to position. And this is where any of these real functions, real sinusoidal functions, will not fulfill this role. Because when you take the derivative, you don't get the same function back. So it's not a momentum eigenstate. Only this form of solution, with the complex exponentials, will fit this description. So when you imagine taking the value of momentum out of these solutions, you'll find that this is the positive momentum and this gives you the negative momentum. And by plugging this into this expression here, you can figure out that, where do I write it? Let me erase this. You can figure out that this coefficient here, k squared, is equal to um, 2me over h bar squared. So, so you take the square root to get k is equal to square root of 2me over h bar squared. So with that, I think I have enough information to write in what the general solution with the positive value of momentum is. It's exponential of plus I times the k, which would be square root of 2me. And if I wanted to, I can just put h bar outside of the square root, be h over 2 pi. Okay, oh, and I need to multiply this by x. So this is the general solution with the positive value of momentum. And the general solution with the negative value of momentum is exactly the same, except for the minus sign in front of imaginary I. Oops, minus. Okay, I'll submit that along with the next one. It says for the region x greater than 0 on the right hand side, the Schrodinger equation takes the form this. And oh, yeah. And if you carefully compare A and B, really nothing much has changed because E was positive and E minus U naught is also positive. So in terms of qualitative features of solution, nothing much has changed. So when we write down, again, my apologies for the noise outside. When you write down the solution with the positive value of momentum, oh, that's just gonna be basically this solution with E replaced by E minus U naught. So let me do that. Minus U naught. Okay. Hopefully there's a way to, yeah. If you don't know how to type in U naught this way, then there's the equation palette. All right, let me submit this and see. Okay, my apologies for the noise that must be coming through the noise filter. The car outside is unreasonably loud. Okay, so yeah, correct answers. Yeah, so those are the general forms of the solution, and this is where it's getting at. With above results, our general solution to the Schrodinger equation is this form of solution, where you've written down psi one and psi two, both in terms of positive and negative momentum. Wonder. Let me pause the recording for a bit because, sorry, the outside it's so loud I can't focus. All right, I closed the window and I think that should help a little bit, at least enough that noise filtering um, filters out the car noise outside. So, sorry, this is being recorded and I'm not planning on editing it, so I shouldn't say any profanities here. Um, So, yeah, that's the general solution. We have that. At least we don't have it written down, but we know what that will be if I need to write it down anywhere. So now it says we need to determine the coefficients A, B, and C to find the particular solution. We do this by applying the two boundary conditions that the wave function is continuous. So this is one of the equations we'll be writing down, and the derivative of the wave function is continuous. Then this is something that applies in other cases, not this particular case. So this is the expression that will apply. It says applying the boundary conditions result in a system of algebraic equations involving coefficients A, B, and C and other parameters. In order to save a little bit of writing, use the following constants to simplify the other given constants in your expressions. I think K1 is already what I was using as K, and K2 will be well, what I can use for in region 2. So let me write in. So this is region 1 and this is region 2. Okay, and yeah, and in parse it's calling for the ratios B over A and C over A. And this is because this is covered in the lecture, and this is how it boils down to. When we, oops, let me just close that. When we write down our boundary condition equations, we have two equations, but we have three unknowns, A, B, and C. So we cannot eliminate all of them. And in fact, the choice we make is to express the other coefficients as in units of A, so that that's the way to get to reflectivity or reflectance. So let's go through the steps here. I need to apply the boundary condition. So let me first write down our general solution so that I have something to refer to. And I think I'll want to first erase everything here. Oh, this is taking way too long. Let me see here. All right, so let me write down my wave function. Psi of x is equal to, depending on the value of x, if x is negative, then it's going to be a times e to the, and using the coefficient defined for us, e to the plus I k1 x plus b times e to the minus I still k1 x. This is for x less than 0. And for positive values of x, it'll be c times e to the plus I have to be careful here, k2 x. And we don't have left traveling solution because we are setting our initial condition so that particle is instant from left. Okay, for x greater than or equal to 0. Okay, the car has moved away. Let me pause the recording briefly and I will open the window back up. Okay, resumed. It's not as though you can see the open window, but it matters to me that it's better with my window open. Okay, so that's my general solution. So let me apply the boundary condition and write down the forms of the algebraic system of equation that results from applying the boundary condition. So the boundary condition 1 is the continuity of the wave function. So I end up saying at x equals 0, the form of wave function on the negative side should equal the form of wave function on the positive side. So I'm just going to plug in x equals 0 as I go. So it'll be a times e to the ik1 times 0. So e to the 0 is going to be 1. So it's just going to be a times 1 plus b times, oh, that's going to be 1 again. So, all right, let me just make this simpler. So it's going to be a plus b is equal to, the right-hand side will be c times e to the 0 or 1. Okay, that's the first equation, simple enough. For the second, okay, so I'm going to do two things at the same time in my head, just saying it out loud. So I need to take the derivative and then plug in value of x equals 0 for the second boundary condition. And because these are all exponentials, taking the derivative will be easy enough. So when I take the derivative first term, I get from the chain rule, a factor of ik1 coming down. So it's going to be ik1 times a times e to the 0 or 1 plus for the second term, oh, it's going to bring down a factor of minus ik1. So let me get rid of this plus and just plug in minus ik1b is equal to c, taking the derivative here, I get ik2. So ik2c. Okay, so I think I can simplify some things, pre-simplify to make things a little bit easier. So I can cancel out I from every term in the second equation. So I get k1a minus k1b is equal to k2c. Okay, so in trying to solve for b over a and c over a, I guess it's simplest to divide out a. Then I get 1 plus b over a is equal to c over a. And here, let me divide it out by k1a, for fun. I think that's gonna be fun. 1 minus k1's cancel, so b over a is equal to k2 divided by k1, k2 divided by k1, c over a. All right, I think here is I see a bit of an easier way to solve for c over a, because for c over a I can do linear combination. I can take this whole thing, add it to the equation above, and if I do that, this is what I end up with. So 1 plus 1 gets me 2. Sorry for the pause, I was sneezing. um, um, b over a minus b over a gets me 0. So, well, 0 is equal to the right hand side, c over a plus k2 over k1 c over a. Or factoring out c over a, it's 1 plus k2 over k1 c over a. So that gives me the answer of c per a is equal to 2 divided by 1 plus k2 over k1. Seems simple enough. Let me plug that in, see what I get. 2 divided by 1 plus k2 over k1. Okay, let me see if that's the right answer. Good, it says it's right. So what I now can do is I can actually solve one of the two equations for example, this equation for b over a, and plug in c over a that I just solved for. That would be the quickest way to get an expression for b over a. And although there are two different ways to calculate b over a, I think they will end up giving you the same value anyway. So one way of getting at b over a is to solve for that here. So c over a minus 1, c over a minus 1. Okay, let's plug in c over a. That's 2 over 1 plus k2 over k1 minus, and I can write 1 in, can I write it in an interesting way? Well, let me give it a try. So to try to write it in an interesting way, I can write it down as 1 plus k2 over k1 over 1 plus k2 over k1. That is a way of writing 1. Same numerator, same denominator. And now taking this difference here, I get on the numerator 2 minus 1, so 1, and then minus k2 over k1. k2 over k1 over, on the denominator, 1 plus k2 over k1. Oh, I'll bet I can simplify it even more. I can multiply top and bottom by k1. And when I do, I'll get this. K1 minus k2 divided by k1 plus k2. I think I like the symmetry of this solution. So let me plug that in. I think there are other possible ways of writing this, but this will work. Let me plug that in. K1 minus K2 divided by K1 plus K2. Yeah, and I don't know if it would matter, but K1 is greater than K2, so this would be a positive coefficient. But I think in this particular case, negative coefficients are also allowed. So the fact that it's positive here, it might have some meaning, might not. Here, that's just for my like. All right, I think that looks good enough. And it says above ratio are reflection coefficient and transmission coefficient. The reflectance defined as ratio of reflected intensity is given by this. Calculate the numerical value of reflectance if E is twice as U naught. So I'm just staring at this and trying to compare. If E is twice U naught, then I think I can say this. Look, I can say that K1 will be square root of 2 times K2, I think. Yeah, I think that'll all work out. So I think that's enough to calculate B over A squared. Let me do that on my calculator. Um, so um, I can kind of see that all the factors of, because I'm taking a ratio, let's say unit of K2 will cancel out. So I can just do K1 minus K2 as a square root of 2 minus 1. Okay, that's a value divided by square root of 2 plus 1. My apologies for the plane noise. Okay, I get, oh wait, that's just the ratio. I need to take the square of it to get what's wanted here. So take the square, 0.0294. That seems rather small, but all right. And then what is the reflectance if E is equal to U naught? If E is equal to U naught, well, K1 would be infinitely greater than K2. K2 would be 0. So this expression reduces to K1 over K1, so 1. Uh, yeah, I hope that makes a physical intuitive sense. Yeah. And you can kind of see from these two numbers plugged in how difference between E and U naught the affect the reflectivity. You can almost look at it this way. So the wave that's incident, it has some wavelength. And what happens when it hits the boundary is because the energy difference is now smaller, the kinetic energy less, so the wavelength gets longer. And what you are seeing is that the greater incident energy is, the smaller, relatively speaking, this change is. So the less effect you get, less reflection you get. But in the limit where this energy is barely above the potential energy, then this wavelength suddenly goes from something that was finite to something that's infinitely long. So it's like hitting a immovable brick wall. It bounces all back. So so yeah, that's a reflection from a step potential. Probably the simplest possible case. The next two examples will be slightly more complicated. So next two. Okay. Yeah, this is tutorial building on the part one of this series. And I think I remember there are three parts. This is the second part. uh, so we are solving. So let me do it this way. I'm gonna take the thing I wrote before, and I'm just gonna make the necessary modifications to make it match this question. So this is gonna be for question 10. We are solving Schrodinger equation for the same potential as before. Una is past constant. We'll solve the Schrodinger equation for instant particles of energy less than the potential barrier. Okay, let me reflect the change here. Oh, gonna change my eraser. It's annoying me that it's not a stroke eraser. All right, so my energy, wait, let me erase this stuff. So now my energy looks something like this. Some energy less than u naught. Um, we won't repeat the solutions for x less than 0 region, which remains unchanged, and the wave function is, yeah, the same thing we had before. Nothing for the negative x region needs to change. So we'll leave those alone. Stroke eraser, stroke eraser is a different kind of annoying. Let me change it back to. All right. Now refer to part one of this tutorial series for general solutions. Yeah, have that. What is new now is the general solution for x greater than 0, where the Schrodinger equation is this, and now E minus U naught is negative. So this quantity as a whole is now positive. So you have a situation where if you take the two derivatives, you will get positive coefficient times the function back. So so in cases like that, so where the differential equation you have is of this form with positive k, the solution that you will get will actually look like this. It's gonna be coefficient times the real exponential solutions, e to the plus kx plus b times e to the minus kx. And so there are two potential solutions, and that's why the question tells you to find the solution exam인데 you'll find that one of them diverges while the other does not. Write down below the solution which does not diverge in terms of the parameters given above. So looking at this here, the solution that does not diverge is the second one because my x goes from 0 to infinity. So x equals 0, both are fine. As x goes to infinity, only the second term is what does not diverge. So I need to make the first term go to 0 and say that this is equal to exponential of, and this k here is the square root of all of this. So let me write it as square root of 2n, and I'm gonna swap the order u naught minus e so that it looks manifestly positive. Divide by 2 h bar or h bar squared that was under the square root, so it's outside the square root, so it's no longer squared. All right, so that's my k, and times oh wait, sorry, it should have, the way my k should have been is k squared. Trying to follow the same convention I was following with the other one. So okay, there should still be x here. Oh wait, and I forgot the minus sign. Yeah, minus, so that this looks like an exponential decay. Okay, let me check that that's correct. Because if it's not, then good. Okay. With the above results and results from part one, our general solution to the Schrodinger equation is, yeah, same as here. Let me change the parameters here, and looks like k2 was defined the same way I defined the capital K there. So so here all I have to do is replace plus I with minus k2, and it'll be basically what I wrote down. Okay, so that's the general solution. We need to determine the coefficients to find the particular solution. We apply the same boundary conditions, continuity of the wave function, and continuity of the derivative of wave function. So applying the boundary condition results in, yeah. At some point, I hope this becomes mechanical. So so the first boundary condition, I don't think it changes at all. When you're plugging in x equals 0, then it doesn't quite matter that whether this is complex or real exponential. So first equation doesn't change. But the second equation changes. So the left hand side, yes, okay. I think what I did in canceling out the i's, that's gonna be no longer valid. So let me rewrite down the second equation carefully so that everything is correct. So again, doing two things at the same time. I'm taking the derivative of the wave function and then plugging in x equals 0. So derivative of this brings down a factor of ik1. So ik1 times a, and when you plug in x equals 0, you get 1. And then minus ik1 times b, and when you plug in x equals 0, you get 1. And now for the right-hand term, derivative here is minus k2. Okay, so minus k2 times c, and then when you plug in x equals 0, you get 1 again. Okay, so it looks like really the only thing that changed is this one. So that means when I divide up by ik1, or sorry, ik1a, I need to make sure to write it down correctly. So the left-hand side is fine, nothing needs to change here. And what's changing here is on the right hand side, on the numerator, I should have minus k2, and on the denominator, I should have I k1. Okay, it's a very, very subtle change from what it was before. Um, so now in this question, it looks like the question isn't asking for c over a, but just b over a. So I'm trying to think through if I think we'll still go through the same steps as before, because even though I don't really need C over A in the end, I think the linear combination here is a more elegant way to kind of get to my answer. So I'll just keep the same, more or less the same expressions. I'll just modify the parts that need a modification. So this should be minus k2 over I k1 C over A. So C over A is 2 divided by 1. And really, this minus 1 over I, that when you rationalize it, multiply top and bottom by I, what it ends up being is actually plus I. So let me actually put that here. So it's 1 plus I k2 k1. Yeah, sorry, my eraser's not working all that well. But it's 1 plus I k2 over k1. Okay, so my first equation didn't change, so b over a is still c over a minus 1. Now, c over a, what used to be 2 divided by 1 plus k2 over k1 is now 1 plus I k2 over k1. Now, you might ask, what difference does it make? Is it the same? Well, let's see. I'll just work through the algebra and see if there's a difference. So for the one that we are subtracting before, our convenient form of 1 changes. It's going to be 1 plus I k2 over k1, 1 plus I k2 over k1. So when you take the difference, let me correct the denominator here. This is 1 plus I k2 over k1, and numerator 2 minus 1, 1, and then I have minus I k2. Okay. This is, I think, where things get interesting. Minus I k2 over k1. Yeah. So before it looked like this, completely real coefficient with numerator that was difference and denominator that was sum. with these changes, what's different is that it looks like numerator is k1 minus I k2, and the denominator is k1 plus I k2. And the special feature here is that for all values of k1 and k2, these two coefficients have the same magnitude. You can actually see that. Do this calculation yourself. B over. Oh, wait. Sorry. Try do that. Let me answer the question that it's asking. B over A. So the question is minus I k2. Oh, we forgot to start the parenthesis. Divide by k1 plus I k2. So that's the coefficient. It looks like it's a subtle, very subtly different from our previous answer. And the subtle difference actually matters a lot. Because it says check for yourself that well, I don't, I hope you can see it intuitively. But what it says is that this is the case in all cases for all values of k1 and k2. And this is how this is intuitively correct. When you have a situation like this, where incident particle doesn't have enough energy to overcome this barrier, you should expect the particle to all bounce back. And this result here is saying that it does. So that's what I mean. Intuitively, this result is what you should hope to see. Now, part C. The surprising result in this part is that even though the energy is less than U naught, so this barrier represents the boundary of the classically allowed region and the classically forbidden region. And in quantum mechanics, you have non-zero probability of finding particles in the classically forbidden region. So it's asking find the length L at which the amplitude of the wave function in the region x greater than 0 has been reduced by a uh, reduced by a factor of e from initial amplitude c. Oh, I think it's giving us everything here. So we know that the wave function in the positive region is c times e to the minus k to x. Um, so so we are starting from c, so that's good. And um, and yeah, so all that this expression is saying is so actually that tells you immediately what the value of L should be in terms of K2. Um, L is 1 over K2. When X is equal to 1 over K2, this is gonna be equal to C divided by E. So L is 1 over K2 in terms of given parameters. Oh, I guess I can answer in terms of K2. I hope. 1 over K2. That's it. Yeah, I hope. Um, yeah. I wonder if this question accepts the long form as well. Um, or I'll check it later. So you could also, I think, express K2 in terms of all these. And I think all the variables that are defined, there's enough of it that you can actually write out what K2 is. I will just check the code to make sure that this question accepts both answers. I mean, this is the simpler form, but I get it if you want to give the longer answer. Um, yeah, and the last question is connected to the idea of quantum tunneling. Okay, let's move on to the next question. Question 11. Okay, it says the tutorial is building on parts 1 and 2 of this series. Yeah, this is the third in the three-part tutorial. This tutorial will only cover the parts that need to change and ask you to recall earlier results. We are solving Schrodinger equation. Oh, yeah, so here the potential is actually stepping down. I think that's a beginning of a change that I should start out well, big enough for change visually that I should start a new question or new space. So this is question number 11. And in this question, oh, wait, let me redraw it. In this question, at x equals 0, my potential starting at 0, it drops to the value of minus u naught. And then it continues to be constant at that value. Okay, yeah, where u naught is positive, so the potential energy is negative for values of x greater than 0. A particle traveling to the right would experience an increase in kinetic energy. So if I have a particle of some energy E coming in, the kinetic energy is this difference here. And as it goes across this step down in potential, kinetic energy would increase. The quantum mechanical result you will derive below illustrates how results of wave mechanics contradict your classical intuition. We want repeat the result. Yeah, so let me, yeah, so I'll write down that form of the function when we get to that part. And for now, let's answer the next part. Um, what is the general solution for x greater than 0, where the Schrödinger equation is this? Oh, I think qualitatively it's actually same as, so let me write down the solution for region 1. So solution for region 1 is equal to a e to the plus ik1 x plus b e to the minus ik1 x for x less than 0. And in region 2, it's gonna be basically the same solution, same oscillatory solution, because E plus U naught is positive as E was. So this is gonna be C times E to the plus ik2x, where I have to be careful. So x greater than or equal to 0, where I would say k2, this is 2, k2 is equal to square root of these coefficients other than minus. So square root of 2m e plus u naught divided by h bar. So exponential of plus I k2 square root of 2m e plus u naught whole thing divided by h bar, or h over 2 pi times x. All right, that should be the solution. And again, we are ignoring the leftward traveling solution because we're assuming particles are incident from left. Okay, so with the above results and result from part 1, our general solution is this. Now we need to determine coefficients A, B, and C. I hope this is beginning to sound repetitive because it quite is. Applying the boundary condition, we say the wave function is continuous, and we say the first derivative of wave function is continuous. So let me write down those equations that you have seen me write down like 2 previous times. So the applying the boundary conditions results in system of equations, and K1 and K2 are defined the way I've already been using. So let me write this down here. The first boundary condition, the continuity of wave function. So at x equals 0, all these exponentials are just gonna be 1. So it'll be a plus b is equal to c. Boundary condition number 2, the continuity of the derivative. So, oh, this is gonna look identical to part 1. So let me just finish writing it down. ik1a minus ik1b is equal to ik2c. And again, i's cancel out because it's in every term. And I can simplify both of them this way. dividing out by a, 1 plus b over a is equal to c over a, and dividing out by k1a, 1 minus b over a is equal to k2 over k1 c over a. All right, the question says solve for the ratio b over a. But like with before, I think I'm gonna find it easier to just solve for c over a first, because it's just so much easier to add this to the above equation. C b over a cancel out, solve for c over a, and so let me just go through that route again. Um, so adding the two equations, I have 1 plus 1 to b over a minus 1, 0 is equal to uh, c over a plus k2 over k1 c over a, or factoring out c over a, 1 plus k2 over k1 c over a. Um, so solving for c over a, I get c over a is equal to 2 divided by 1 plus k2 over k1. I can plug this into the first equation where I've solved for b over a. Solving it for b over a, I get b over a is equal to c over a minus 1. So c over a is going to be 2 over 1 plus k2 over k1 minus, let me subtract out the interesting version of 1. So that's going to be 1 plus k2 over k. I think I've done all this before. Nothing algebraically has changed. So let me just finish this and we'll see what has changed. 2 minus 1, that's 1, minus k2 over k1, and the denominator is 1 plus k2 over k1. And I can simplify this a little bit more, multiply top and bottom by k1. I have k1 minus k2 over k1 plus k2. And superficially, it might look like nothing has changed from part 1. And in some sense, you're right. B over A is really the same value, same algebraic expression that it was before. This is what has changed. In part 1, I made the remark that B over A is positive. Take a look here. Is B over A still positive? I hope you notice that K2 is actually larger than K1. So B over A is actually negative. And yeah, it's reflection coefficient, which may be complex or negative depending on phase shift. And this is the explanation. Negative coefficient represents a pi phase shift. As you can see, to the I pi is equal to minus 1. I think in optics, we gave this effect without proving it. In optics, we told you that depending on the direction of change of index of refraction, either there's a pi phase shift or there isn't. And this is proof showing how in one context there is a pi phase shift if the potential energy drops. What this ends up doing is this. So, if we imagine a wave function solution, this drop in potential energy increases kinetic energy, and it causes the wavelength to be shorter. And what this result is showing is that if the wave goes from region where it has longer wavelength to shorter wavelength, then the reflected wave experiences a pi phase shift. It's quite analogous to what you have seen in the case of optics, except in the optics we didn't bring in quantum mechanics. All right, let's finish it here. B over a squared. I think that's just gonna be this whole thing squared. I don't know. Nothing's gonna be any more. I don't know. We can just take the whole thing and square it. um, yeah, that is correct. It doesn't really simplify any more than this, so I wouldn't do anything more. Use the result above to answer below qualitative conceptual questions. Which of the following conditions describe a condition when nearly all instant intensity is reflected? That is, b over a squared is greater than or approaches 1. Hmm. So what I would want to happen is, so K2 is always gonna be greater than K1 in this scenario. So I would want K1 to be much smaller compared to K2. So for that to happen, oh yeah, the potential drop should be as great as possible. So that K1, whatever it is, in comparison to K2, it's much smaller. Yeah. Which of the following conditions describe a condition when nearly no incident intensity is? I think it's intuitively easy to get this. If a U naught goes to zero, then there's barely any kind of sudden shift here. So it makes sense that less and less will be reflected. And yeah, this is just a closing remark that when you think of this in thinking when you think of this in comparison with wave mechanics, for example, wave optics, then nothing here is actually mysterious. It's quite what you would have expected. Um, the kind of paradoxical result comes in if you try to think of a classical analog of this. And simple answer here is that there is no classical analog. Classical mechanics is an approximation of quantum mechanics, and it's not, as with any approximations, it's simply not expected to have usable analogs in all cases because it's not a complete theory. All right, so that's done. Um, Question 12, tunneling estimate. Calculation of tunneling probabilities. It's fairly involved. Yeah. Uh, yeah. So I think in this question, I actually have you just to do a simple estimate. However, we can do a simple rule of thumb estimate, which will be quick and still good enough to give you a fair intuition. Yeah. So where U naught is greater than E, yeah, it takes this exponential decay for an electron of energy incident on a height of 3 eV. Um, I feel like this is something that you can just to do yourself. Well, I'll do the calculation, but I won't give a whole lot of explanation. Will that make sense? Let me just see. Um, and yeah, let me plug in the numbers with Wolfram Alpha, and I can just calculate the answer without a lot of explanation. That'll be pretty quick. So I can just do this exponential portion of calculation. Um, well, the exponential expression, it's gonna look like exponential of minus times minus a square root of 2 times electron mass. I do need that. Times the U naught, which is 3 eV, minus the instant kinetic energy, 1.4 eV, close square root, divided by h bar. It, that times x. That's the whole exponential thing. And what I'm looking for is to find the distance x inside the barrier where psi of x has dropped to 0.47 of the initial value. Okay, so what I can imagine is I'm taking natural log of left hand, right hand side. Right hand side will just turn into this. And left hand side will be, or I should have imagined the moving dividing by a, then left hand side will be natural log of 0.47, and that's going to be a negative quantity. That's the left hand side, that's the right hand side, and we are looking for value x. So I'm going to just divide left hand right hand side by this coefficient here. So what the calculation only works out to be is taking natural log of 0.47, dividing out by this, and this division should give me x. Okay, let's enter it and see. Um, yeah, it looks like it did all the calculation. So yeah, 1.165 times 10 to the minus 10 meters, or in terms of nanometers, this would be 0.117 nanometer. And yeah, you can use this to estimate tunneling probabilities. So it ends up being, um, taking 0.47 and squaring it. Yeah. So let me do 0.47 square, or 0.2209, 0.2209. And yeah, and this bit is telling you how this estimate, it's definitely off. This is the quote unquote correct result. But it gives you close enough of a result to get you some sense of, is there significant tunneling probability. And the terms that we are neglecting that it's kind of referring to here is the reflected term. When you look at the textbook's treatment of quantum tunneling, which you actually will have to look at to answer this question, it'll you can see what I mean by reflected term. It's gonna look like, oh, why does it do this? um, so the reflected term looks like, wait, 7 quantum tunneling of particles. So when you see the textbook set up the equation in this barrier region here, it sets up the equation so that you have solutions. In region 2, where's my region 2? Wait, do they never write down the region 2 solutions? Oh, how? They write down region 1 and region 3? Oh wow, they never actually work out this solution. Or, oh, no, no, no. Oh, there it is. Okay. That's the region 2 solution. And in the region 2 solution, so we have been using only this term, the term that does not blow up when x goes to infinity. And when you have the finite barrier region, you cannot simply get rid of this. You have to include that, and that's what I'm referring to as reflected wave. Kind of looks like that, but anyways. So including both of these terms changes the tunneling probability. And there's actually something like resonant. Uh, so tunneling probability, it's not a monotonic function of something that decreases as a function of the thickness. At certain thicknesses, there can be a resonant amplification of the tunneling probability. So in any case, so you can follow the textbook derivation, and for the purpose of this question, really, all that you need to use is this equation here. I think E over U naught is simple enough. You are given E and U naught, and you need to track down how this beta is defined. That beta was defined um, in terms of that. Um, yeah, so take the square root of that, um, and then you can solve for it. Um, I guess okay. I think it's worth doing. So let me do that. Sorry, my eyes are kind of glazing over, but I think it's worth doing. So let me do that. So for this question, I do expect you to refer to the textbook's answer, because I definitely don't expect you to reproduce all this calculation, because The reason we didn't cover it in lecture was redriving this would have taken a whole day, whole hour, or some amount of time that we don't really have. So for the purpose of answering this homework question, you'll need this equation, that's one, and you need the one that defines what beta is. That's not something that I would have memorized. So you need a definition of beta. And I think once you have that, then you have everything you need to solve for what they are asking for. They are asking for the thickness of the barrier, um, which would match the tunneling probability. That's T L over E. So let me just double check that, and we'll do that. Um, T L over E. This is the uh, tunneling probability. Um, yeah, and I think we can use this one. 2.5% is low enough that this approximation is probably valid. But if it had a higher tunneling probability, you would want to use this. So, looking at the expression here, my goal is to so beta is a parameter that I can actually get numerical value of. So my goal is to given this t, my goal is to solve for this L here. So let me just put everything together. So e to the minus 2 beta L is equal to everything on one side, um, t divided by 16 e over u naught, 1 minus e over u naught. Okay, now I can take the natural log of both sides. Doing that gets me minus 2 beta L on the left hand side and the natural log of that big thing on the right hand side. So solving that for L gets me um, minus 1 over 2 beta times natural log of t over 16 e over u naught 1 minus e over u naught. And beta is, let me put in the expression for beta, then it's 1 over 2 times the natural log of 1 over beta, which would be um, h squared the square root it, so h divided by square root of 2m u naught minus e. Okay, I think I have that's something I can just plug in numbers to. So let's do that. Um, so plug in the numbers here. It's gonna be minus 1 over 2 times natural log of t is 2.5%, or that should be 0.025 divided by 16 times the instant energy. I'm just gonna write it as 12 divided by 15.5 because the electron volt units will cancel out. Times 1 minus, again, 12 divided by 15.5 because electron volt units will cancel out. Okay, that's the whole thing under the natural log times, and now I need a Planck constant, h bar, divided by square root of 2 times electron mass times, and here I do need to plug in the unit, 15.5 eV minus 12 eV. Okay, I think that's everything. All right, let's see what we get. Yeah, everything is understood correctly, and we get something in the unit of length, 2.461 times 10 to the minus 10 meters, or this should be a 0.246 nanometers. Yeah. So, it's a complicated formula, and again, it's not something that I would expect you to read right. And I think this is quite similar to the previous question, except maybe a little easier. So I'll leave this for you. Um, yeah. So I think that's all the questions. So in the virtual class session today, I will definitely go over. I'll probably be redoing some of these questions. This recorded video was created as a backup for any questions I didn't get to cover in the 1 hour, because this entire video, well, it's about an hour. So, anyways, thank you for watching. I'll see you later. Bye.